did the last time. If we compare continuous time signals and discrete time signals, the Fourier transform for a continuous time signal is an integral minus infinity to infinity x of t e to the minus j omega t dt, whereas the Fourier transform for a discrete time signal is a summation as expected. This is x of n e to the minus j n cap omega. N goes from minus infinity to plus infinity. This is the difference. The difference is that not only it is a summation, but it also is periodic in omega. That is, if you increment omega, increment or decrement omega by 2 pi or any multiple, any integral multiple of 2 pi, the value remains the same. And the other thing is the inversion integral x of t. In the continuous time case, it is 1 by 2 pi. Again, the integration is from minus infinity to plus infinity. Capital X of omega e raised to the j omega t d omega. In the discrete time case, it is again an integral, but the integral is over only one period. 1 by 2 pi integral over one period. Capital X of omega e raised to the j n omega, then d omega. All right. So the difference is that this integration in the continuous time case is for all values of omega, whereas in the discrete time case it is only over one period. And the reason is obvious or transparent in this, that capital X of omega is periodic, and therefore it only makes sense to integrate any function which involves x of omega over one period. It doesn't make sense to integrate from minus infinity to plus infinity. One should also recall the interpretation that I had given last time of capital omega. Capital omega, the basic range is from 0 to pi or minus pi to pi, or from any value to that value plus 2 pi. That is the basic period. The interpretation of capital omega is, since the range of variation is only over 2 pi, it is obviously a normalized frequency. It is obviously a normalized frequency. And the relation between actual frequency and capital omega is that it is actual frequency in radians multiplied by capital T, where capital T is the sampling interval. That is, it is twice pi actual frequency in hertz multiplied by capital T. Capital T is the sampling interval. What would 1 by T be? 1 by capital T, sampling frequency. And if we denote that by Fs, then obviously it is 2 pi actual frequency divided by the sampling frequency. And you notice that indeed it is a normalized frequency, because it is a ratio of two frequencies. This interpretation shall be very useful in digital communication, because, and it offers an advantage that we can work in terms of a normalized frequency capital omega, and the range of capital omega that we need to consider is only over one period, and the period is 2 pi. That's also a beautiful number, twice pi. Well, we also recall a few examples that we did, and one of the interesting examples that we did for evaluating Fourier transform, all of these shall be useful today, so I am recalling these factors. E to the j omega 0 n, this signal is not necessarily periodic in n. Isn't that right? It is not necessarily periodic unless omega 0 by 2 pi is a rational number. This is not periodic. Nevertheless, its Fourier transform is periodic. Well, the Fourier transform, if I write it down, it is twice pi delta omega minus omega 0 minus 2 pi L, where L goes from minus infinity to plus infinity. We had derived this. We had derived this not by the direct route, but by the reverse route. That is, we assume that capital X of omega is equal to this, and then we applied the inversion integral. That is, we found out x of n as 1 over 2 pi integral over 2 pi capital X of omega e to the j n omega d omega. We found out that x of n is exactly equal to this. We went through the converse rule because it is more convenient. The direct evaluation is somewhat difficult. Well, the point that I want to mention is that alright, to make it more clear, you recall that if we have a signal, a periodic signal e to the j omega 0 t in the continuous time domain, then this is periodic. This is periodic for all values of omega 0, alright. The difference between this, the discrete time case, and the continuous time case is that e to the j omega 0 t is periodic irrespective of what omega 0 is. E to the j omega 0 n is not necessarily periodic. It is periodic only if omega 0, capital omega 0 over 2 pi is a rational number. Now, you recall that the Fourier transform in the continuous time case, this was simply 2 pi delta of omega minus omega 0. There is just one delta, that is the Fourier transform of the exponential function e to the j omega 0 t is just one impulse at omega equal to omega 0. On the other hand, irrespective of whether this is periodic or not, the Fourier transform of this single exponential function is a chain of impulse functions, and this chain this repeats at regular intervals, which means that this spectrum is periodic. Alright, there are many differences which you have to notice very carefully. You also have to notice one other important factor, that delta n, if I write delta n is an impulse in the discrete time domain, and its value is 1 occurring at n equal to 0. Whereas, when I write delta omega, alright, what is this? This is not a discrete domain. Capital omega is a continuous variable. Small n is a discrete variable. It can only assume integer values, whereas capital omega is a continuous variable, and therefore delta omega is indeed a delta function. The area defined by its area under the curve is equal to unity. You must notice these differences very carefully because it is very easy to get lost. I repeat, the function is an extremely important function, that is why I repeat again and again. The function e to the j omega 0 n is not necessarily periodic, but its spectrum is periodic and consists of a chain of impulse functions in the continuous omega domain, and therefore it should be represented by an arrow. We also introduced the discrete Fourier series, DFS, and we said that if x of n is periodic, x of n is x of n plus n, then x of n can be expanded in a Fourier series of finite number of terms. This is the difference between continuous time Fourier series. Continuous time Fourier series, if x of t is equal to x of t plus capital T, then x of t can be written as summation a k e to the j k omega 0 t, k goes from minus infinity to plus infinity, where omega 0 is equal to twice pi over capital T. Alright. This is the continuous time case, CTS, continuous time signal. In the discrete time case, on the other hand, the Fourier series is finite. It only goes over a length of capital N. In other words, if you start from n equal to 0, you go to capital N minus 1. And therefore, what we get is ak e to the power j, omega 0 is 2 pi over n capital T, and small t is nt. This is how we found out. Well, there must be a k, I missed that, j k. Let me write it again. This would be a k e to the power j k. Instead of omega 0, we have 2 pi by n, capital N being the period. Capital T you can assume to be 1 normalized, or it cancels out with small n times capital T. So, this is my Fourier series, and k now goes from 0 to capital N minus 1. There is nothing sacred about the lower limit and the upper limit, but the difference must be equal to capital N minus 1, because 0 is included, the number of samples is capital N. Well, this result can be interpreted in various ways. One of the ways is to say that in the Fourier series of a discrete time signal, there are only capital N number of distinct frequencies. Agreed? This is why you get a finite Fourier series. The number of frequencies or the number of harmonics, distinct harmonics, is only capital N, including 0, DC. K equal to 0 is a DC term, that we get A0, and then you have A1 e to the j 2 pi by n. This is the interval between two successive frequencies, and then you have its harmonics, twice 2 pi by n, 3 times 2 pi by n, up to capital N minus 1 2 pi by n. All right. So whereas in the continuous time signal, the Fourier series is infinite in extent. You can have infinite number of harmonics. The number of harmonics in the discrete Fourier series is finite, and the number of distinct frequencies is exactly equal to capital N, which includes 0. Now, in a manner, in a style which we have worked out earlier, it is very easy to invert, that is to find out what AKs are, what the coefficients are. In the continuous time case, you required an integration. In the discrete time case, it simply is a summation. What you do is you multiply x of n by e to the minus j k 2 pi over capital N times n, and then sum up over n from 0 to capital N minus 1, that is over one period, and divide by capital N. This is the formula for the coefficients. There are 2 points that I wish to emphasize. One is that this is not a matter of definition, it can be derived, and the derivation is very simple. What you do is you take x of n, this expression, multiply by e to the minus j r, some r, 2 pi by n. All right, let us look at this. X n is summation a k e to the j k 2 pi by n times capital N. K goes from 0 to n minus 1. Then what we do is we multiply x n by e to the minus j, some other integer r, I do not want to confuse with k, r 2 pi by n, n. I believe I have done this earlier. If I have not done it, you do it. And then we sum up from n equal to 0 to capital N minus 1. All right. Now, if you multiply on both sides, if you multiply here and also here, you see that the exponential, in the exponential you shall get e to the j k minus r 2 pi by n times capital N, where the summation would be over, have I made a mistake? Okay, summation is over k and small n, all right. They are independent of each other, and the only condition under which this exponential summed up over one period will give you a non-zero value is k equal to r, and that's how on the right hand side you get exactly AR. I urge you to prove this. I shall skip this proof, all right. This is extremely easy. We have done it in the case of the integral. You can do it in the case of the summation, and such a function, such a summation is, you will know later, is called a Kronecker delta. Kronecker delta, exactly like all delta functions, exists only at one point, one value, and k equal to r is the value for this. Kronecker was a mathematician. I just want you to hear the name. We will not go into any details of this. Yes? So we summarize our discussion of Fourier series by saying if x of n is periodic, then x of n can be written as ak e to the power minus j k 2 pi by n times n, where I have made a mistake. There is no minus here, this is plus. Alright, this is a Fourier series, and ak is given by 1 over n summation xn e to the minus jk, now it is a minus 2 pi by n times n, where n goes from 0 to capital N minus 1. Alright, this is my discrete Fourier series. We shall require this a little later. Alright, this is as far as the review of previous day's lecture is concerned. There is just one more thing one needs to do before we go into the further consideration of the periodic signal, and that is the following. You recall that if in the continuous time case that yt, if it is a convolution xt star ht, well, in terms of a system, ht is the impulse response and xt is the input and yt is the output. You recall that if x of t is equal to e to the st, an exponential signal, then y of t is equal to e to the st multiplied by a constant h of s, where e to the st is called an eigen function and h of s is called eigen value. The value of h of s is simply ht e to the minus st dt from minus infinity to plus infinity. Okay, let's see what these relations give in the case of the discrete time signal, discrete time signals and systems. Okay, our y of n, the output here is x of n star h of n, and if x of n in similarity with an exponential signal, if x of n is, let's say, z to the n, well, z can be put as e to the power some other constant. If x of n is z to the n, then you notice that y of n, which is x of n minus k hk, the convolution k equals minus infinity to plus infinity, you substitute x of n minus k as z to the n minus k and all other terms remain the same, then you notice that y of n is z to the n summation k equals minus infinity to plus infinity. What do I get? H of k z to the minus k, and I can put this summation as some constant h of z, and therefore you get absolutely similar relations. That is, in the discrete time signal, if x of n is z to the n, then y of n implicit is one assumption which I have not mentioned. What is the assumption? That it is an LTI system. That is correct. Then y of n is z to the n h of z, and therefore z to the n is indeed an eigen function and h of z is the eigen value, and h of z is equal to summation instead of integral. It would be a summation h of n z to the minus n, z to the minus n, n goes from minus infinity to plus infinity. You notice a very interesting thing, that if z is e to the j omega, if z is e to the j omega, then what is this summation? What is this summation? H of n e to the minus j n omega summed up from minus infinity to plus infinity. This is the Fourier transform of h of n. If z is e to the j omega, then h of z is the Fourier transform of h of n. We shall come back to this relationship later. Now, we are going to discuss a somewhat involved case, an example of a Fourier transform of a somewhat involved case, that is the periodic signal. And notice this carefully. Suppose we have an x of n which is periodic. That means it runs like this: ak e to the power j k 2 pi by n times n. K goes from 0 to n minus 1. X of n is periodic with a period of capital N. Let me write this fully. I write this as a0 plus a1 e to the j 2 pi by capital N times n plus a2 e to the j 2 times 2 pi by n n, and so on up to a n minus 1 e to the j n minus 1 2 pi by n times n. All right. If I want to take the Fourier transform of this, Fourier transform of x of n, what we are considering now is Fourier transform of a periodic signal. Then because Fourier transform operation is linear, we can take the Fourier transform of each term. In this, you recall one fact, that e to the j n omega 0, what is the Fourier transform? It is summation 2 pi delta omega minus omega 0 minus 2 pi L. L goes from minus infinity to plus infinity. If you recall this result, then it's very easy to write the Fourier transform of this. Well, what would be the first term? First term would be 2 pi a 0. What is omega 0 for this term? 0. And therefore, I shall have summation delta omega minus omega 0 is 0 2 pi L, all right, L from minus infinity to plus infinity. I will not write this again and again, I will simply write summation, okay, plus for the next one it is 2 pi a1 summation, I must go to the next page. Well, Fourier transform of x of n is equal to 2 pi a0 summation delta omega minus 2 pi L, L equal to minus infinity to plus infinity. The next term is 2 pi a1 summation delta omega minus, yes, what, 2 pi by n minus 2 pi L, once again the summation is over L, plus 2 pi a2, I will write up to the second, up to the n minus 1th term, delta omega minus 4 pi by n minus 2 pi L, must close the bracket, plus etc. up to 2 pi a n minus 1 summation over L delta omega minus, now what do I have, n minus 1 times 2 pi over capital N minus 2 pi L. You see, not only the spectrum is an infinite number of summation, but there are capital N number of infinite summations, all right. Each of them is an infinite summation, each of them is a chain of impulses. Now, when you put them in the form of a picture, the picture becomes nicer than what I have written here. Let's look at that. Let's look at that. The spectrum. All right, this is my capital omega and this is capital X of omega. For the first term, which is 2 pi a0 summation delta omega minus 2 pi L. For the first term, well, L equal to 0 gives me an impulse here. All right, this is capital omega, and what is the strength? 2 pi a0. All right. Then L equal to plus 1 gives me an impulse at 2 pi. The strength is the same, 2 pi a0, and this is 2 pi. L equal to minus 1, well, somewhere here, let's say, minus 2 pi, the strength is 2 pi a0. And this continues, okay? This continues on this side and on this side also. Let's take the next term, the second term. Let's use a different color. The second term is 2 pi a1 summation delta omega minus 2 pi by n minus 2 pi L. alright. The only difference is that this spectrum is shifted to the right by an amount 2 pi by n, and therefore, and of course the strength is different, 2 pi a1 instead of 2 pi a0. So let me draw this. Let's say this is 2 pi a1, all red colored arrows are of strength 2 pi a1, then I have one here, I have one here, and so on. This repeats. This difference, well, this is 2 pi by n, this is 0. Similarly, if I take the second term, then it shifted to the right by 4 pi by n, and therefore I shall have arrows here. Let's say to bring variety into experience, let's suppose a2 is negative, alright. Then I shall have a 2 pi a2 here, where this is 4 pi by n, I shall have a 2 pi a2, I shall have a 2 pi a2 here. And this repeats, alright. There will be one at 6 pi by n of strength 2 pi a3 and so on, and this will repeat till this point where it would be 2 pi a what? Capital N minus 1, and this abscissa shall be n minus 1 times 2 pi by capital N. Now, don't you see that when you draw all of them, well, the picture becomes full, and all that we have now is, if we take, it is periodic, isn't that right? Starting from 0 to capital N minus 1 2 pi by n, then at capital N, that is at 2 pi, it repeats. It is indeed periodic. We know x of omega has to be periodic, and since it is periodic, all that we have to do now, capital X of omega, I can write a very simpler expression. I can write 2 pi summation ak, yes, delta of omega minus k 2 pi by n, where k goes from, pardon me, then I don't get infinite number of terms. K equal to 0 to n minus 1, all right. And then another summation. Oh yes. Suppose I don't want to use another summation. This is my picture.
X of omega equal to x of omega plus 2.
K minus infinity to plus infinity. Why don't you do that? All right, that will resolve the total issue. I want a simpler expression. I didn't want to use two summations. So I simply raise minus infinity to plus infinity. It being implied that a0 is the same as an, is the same as a2n, is the same as a minus n, and so on. This we know, that there are a capital N number of distinct coefficients only. This simple expression now gives you the spectrum of a periodic function, and you see the spectrum is of infinite extent, but it is periodic, and therefore if you can take a picture of one period, then you know the whole story. This is a very, very interesting result. We shall illustrate this. Let me write it down. X of omega is equal to 2 pi ak. It doesn't matter where we put the summation. K equals minus infinity to plus infinity delta omega minus k 2 pi by n. Let's consider an example. We consider an example of x of n as a chain of discrete time impulses, that is delta n minus kn, where k goes from minus infinity to plus infinity. This is a periodic function of period capital N. All right. If we look at it, the function is like this, n, and we have at, if this is 1, then we have a chain of impulses, chain of discrete time impulses like this. This is all 1, 0, 1, 2, 3, minus 1, minus 2, minus 3. So it is indeed a periodic function. Okay. Now we are required to find out capital X of omega. One of the ways of finding the spectrum is to take the Fourier transform of delta n, which is, what is the Fourier transform of delta n? Unity. If x of n equal to delta n, the Fourier transform is simply unity, because delta n exists at n equal to 0 only. Multiplying by e to the minus j n omega, put n equal to 0, it is simply 1. And then argue what is delta n minus another integer, it is a delayed e to the minus j n, and therefore you can express capital X of omega in terms of a sum of exponentials. This is one way. The other way is to look at it as a periodic function and then get its spectrum. All right. X of n is equal to summation infinity k equals minus infinity delta n minus kn. Because it is periodic, I can write this in the form of a Fourier series. So I write this as ak e to the power j k 2 pi by n times capital N, where k goes from 0 to n minus 1, and then take the transform term by term. You can easily show that ak by definition is x of n e to the minus j k 2 pi by n times n summation n equals 0 to capital N minus 1. All right. Now the evaluation of this is extremely easy. This is within one period, isn't it? Within one period, what is the number of samples? I made a mistake in the previous slide. Yeah, the value would be 1 by n, but why didn't you object to this? This is not correct. This is n, 2n, 3n, and so on. Now within one period, that is 0 to n minus 1, there is only one sample, and therefore if you evaluate this summation, you just put n equal to 0, and therefore this becomes equal to 1 by n. I forgot a factor 1 by n. All right. This exists within this period, only one sample delta n, and therefore the summation is simply equal to 1 by n. In other words, the Fourier series expansion of this periodic repetition of impulses, that is delta n minus kn, k goes from minus infinity to plus infinity, is simply 1 by n summation e to the j k 2 pi by n times n, where k goes from 0 to n minus 1. And you now take the Fourier transform of this. Therefore capital X omega shall be simply equal to 2 pi by n. All right. What do I get? Sigma of delta. Yes, you remember the simplified form, omega minus 2 pi k by n, where k goes from minus infinity to plus infinity. All right. This is the great result that we obtain. X of n, which is a chain of impulses in the time domain, transforms to a chain of impulses in the frequency domain. The nature of these impulses are different from these impulses. These are truly impulses in the continuous domain. That is, this exists only at omega equal to 2 pi k by n, and the area under the curve is unity, whereas this delta n is simply a line of height unity occurring at n equal to 0. So a chain of impulses in the time domain transforms into a chain of impulses in the frequency domain. These are true impulses going to height infinity, 0 width, these are simply lines of height equal to unity. If I plot the spectrum of this, obviously what I get is all impulses shall be of strength 2 pi by n, and therefore what I will have is a fence like this, all right, continuing on both sides, and the interval is 2 pi over capital N. This is the spectrum. The spectrum looks exactly similar to the time domain function except for the arrows. Well, this after this few examples and an explanation about the periodic function, we would now like to study some properties of the Fourier transform of discrete time signals. Sometimes instead of writing Fourier transform of discrete time signals, we abbreviate this as DTFT. I didn't want to use this term earlier because there may be confusion. This is discrete time Fourier transform. If this capital T is not there, let me warn you, the meaning becomes completely different. The DFT, discrete Fourier transform, is completely different from discrete time Fourier transform. As you shall see later, DFT is discrete in the frequency domain also. We will not bring this into consideration at the moment so that there is no confusion. We use DTFT is simply as an abbreviation for FT of DTS. Fourier transform of discrete time signals, we use DTFT, discrete time Fourier transform. Before we start the properties, let me emphasize again that the concepts in discrete time domain are much more simplified. The computation is much simpler as compared to the continuous time domain because integration is replaced by summation. It is easier to evaluate a summation than an integration. However, the mathematics involved and the periodicity of capital X of omega, does create complications. For example, you saw that in sampling it creates aliasing distortion. In reconstructing a signal, in reconstructing a discrete time signal given its spectrum, the spectrum is of infinite dimension and you cannot simply truncate. So there are plus points as well as minus points, but discrete time signal, the characterization and the Fourier transform has to be studied a little more carefully than continuous time systems. All right. Now, one of the properties, the first property that we have already known is that X of omega is periodic with period equal to 2 pi. And the definition of X of omega itself shows that the Fourier transform operation is linear. Second property, FT is linear. Stated in precise terms, it means that if x1 of n and x2 of n lead to capital X1 of omega and capital X2 of omega, then A1 x1 of n plus A2 x2 of n when transformed shall give you A1 capital X1 plus A2 capital X2. This is the linearity of operation. We next study the properties of Fourier transform. If the signal X of n is real, you shall see many interesting properties. First is that capital X of omega, if X of n is real, then it is the same as X star of minus omega. This is one of the properties. And the proof is extremely simple. You notice that capital X of omega is equal to summation by definition x of n e to the minus j n omega, n equals to minus infinity to plus infinity. If I take x star, x of n is real, so the only thing that changes is this sign becomes positive. Is that okay? And I can write this, if I now change omega to minus omega, if I change omega to minus omega, then this sign again changes to minus omega, which is precisely equal to capital X of omega, and therefore the theorem is proved. Alright? X of omega is the same as x star of minus omega. Can you tell me what will be the Fourier transform of x of minus n if x of n is real? Well, it turns out that this is simply capital X of minus omega, and it's very easy to show. Just put in the definition, then you can show that x of minus n is x of minus omega. Let's look at this relation, x of n real, then capital X of omega is summation x of n e to the minus j n omega, n equals minus infinity to plus infinity. You notice that the real part of capital X of omega is simply x of n times, instead of e to the minus j n omega, real part of this is cosine of n omega. And what is cosine of n omega? It is a real function and is even, alright, and therefore real part of x of omega of course has to be real, isn't it? By definition it is even. The property, important property is that if x of n is real, then the real part of its spectrum is an even function. Even function of, even in what? Omega, alright, not in n. No? Isn't it even in n? I put a trap. I am asking the question again. Is real part of x of omega even in n?
Yeah, it is.
It is a function of n. Of course it is a function of n. It is summation x of n cosine n omega. If this function is to be even in n, then don't you have to have constraints on x of n? Only if x of n is even, then it will be true. So real part of x of omega is even in n if x of n is equal to x of minus n. Alright? What?
N is not a variable. X of omega is going to be a function. X of omega is a function of omega only.
Omega only.
Talk in terms of omega only. Sir,
That is correct. So this is a wrong derivation. Capital X of omega, I warned you, I am putting a trap. Capital X of omega is not a function of n at all. Alright, so we cannot talk of capital X of omega being even in n or odd in n. It doesn't make sense. Alright. What can you say about the imaginary part of x of omega? In a similar manner, imaginary part shall contain sine of n omega, which is an odd function of omega, and therefore imaginary part of x of omega must be odd in omega. Alright? Real part of it is exactly the same in the continuous time domain. Alright? Real part of the spectrum is even and the imaginary part of the spectrum is odd. What can you say about the magnitude? Magnitude squared is real part squared plus imaginary part squared. Even squared is even, odd squared is also even, and even plus even is even, and therefore magnitude must be even. The angle capital X of omega, angle X of omega is tan inverse imaginary part divided by the real part. Imaginary part is odd, real part is even, and therefore this must be odd. Alright, these are elementary properties of the Fourier transform of real signals. I also claim that if I take the even part of x of n and make x of n is real of course, then what is its relation with capital X of omega? It is the,
half x omega plus x minus.
that is the real part of X of omega. That is, even part of X of n transforms into real part of X of omega. The proof is extremely simple. You take X of n plus X of minus n by 2. This transforms to capital X of omega, and this transforms to capital X of minus omega, which is simply equal to X star of omega, and therefore X of omega plus conjugate divided by 2 must be the real part. In a similar manner, the odd part of X of n shall transform to imaginary part of capital X of omega. There is a murmur here. J times, yes, that must be brought in. J times imaginary part of X of omega. So, if X of omega, X of n is real and even, can you tell me what shall capital X of omega be? It must be real and even. Okay. If X of n is real and even, then capital X of omega must also be real and even. There are two very simple properties which we shall mention and then complete the class. That is, if X of n is capital X of omega, then X of n minus n naught, that is, if it is a delayed signal, exactly the same way, it would be e to the minus j omega n0 capital X of omega. On the other hand, this is the time shift, sequence shift. On the other hand, if I multiply X of n by e to the j omega 0 n, it is very simple to show from the definition that this will be simply capital X omega minus omega 0. What the thing to be remembered is, if there is a plus sign here, then there is a delay here. Alright. How does this come about? E to the minus j, no, more than duality, even for the first principle, e to the minus j n omega, and this is e to the j omega 0 n. So, you can write the product of these two as e to the minus j n omega minus omega. That is how this comes. The next property in the sequence would have been scaling in the time and frequency domain. That is, you remember that if x of t in the continuous time domain is x of omega, then x of at goes as capital X of omega by a, and the scaling factor is 1 by mod a. Now, this loses its significance in the discrete time domain, because if you have x of n, then what does x of a n mean? Unless a is an integer, it does not mean anything, alright, and therefore the scaling in the time domain has to be viewed very cautiously if it is a discrete time signal. For example, if a is 2, let us say x of t and x of 2t, what does this mean? What is the difference between these two signals? X of 2t is a slowed down or a, okay, x of 2t is a compressed signal. What does it mean? Is it slowed down in terms of a tape recorder speed? Speeded up. Okay. X of 2n on the other hand is not a speeded up signal. X of 2n, what does x of 2n mean compared to x of n? Information is lost. That is, only even samples remain, and therefore the time scaling property has to be viewed very cautiously. You cannot write an analogous expression. What you can write, we shall see the next time.